So during last class, we constructed recursions. Recall the Towers of Hanoi example where we took the actual algorithm and produced a recursive relationship to describe the number of moves that needed to move all the disks from one tower to another. Now, once we have recursion, as I've mentioned before, we can keep building this particular sequence one term after the next. But how do we connect a formula for any particular term, also called explicit formula, with the recursive definition of the potentially same sequence? So this is what we're going to talk about today. Suppose I have a sequence, and suppose that it is defined by this particular formula, which means that I can plug in any value of n, and I will get the nth term. So, for example, I can plug in, let's say, 10, and I can calculate a of 10, so the 10th term in the sequence directly, which if I plug in 10 here, I can see it's going to be 3 times 10 plus 1, so it's going to be 31. On the other hand, I have a recursive definition of allegedly the same sequence. We're going to have to prove it, but let's believe it for a second here. So what this is doing is it's defining the term I in terms of the previous term. So if I were to use this definition to compute a of 10, then this definition would tell me that a of 10 is actually a of 9 plus 3. Now, without knowing a of 9, there is nothing I can do to compute this. So I can go one level further and compute a of 9. I will apply the exact same recursion to compute a of 9, which will be a of 8 plus 3. Now, I still can't quite compute this, so I'm going to have to figure out what A8 is, and so on and so forth. So if I have a recursive definition, if I want to compute any particular term in the sequence, I have to go all the way down to the very beginning. If I have an explicit formula, I can compute any given term directly. What this question is asking is to show that this explicit formula and this recursive definition actually describe the exact same sequence of numbers. Let's try to, first of all, compute the first few to persuade ourselves whether it's even remotely true that this is a possibility. So let's say I'm starting here with 0, right? So let's say I'm plugging in n equals 0. So this sequence will produce A0 being 1. A1, so I will plug 1 in for n, will be 3 times 1, so 3 plus 1 is 4. A2, plugging in 2 for n, will produce A7. A3 will produce a 10, a 13, and so on. What happens if I start using the recursive definition of the sequence? So first of all, notice that there's a small issue with actually applying this recursion. And that is the fact that this isn't actually a complete definition. I am missing an initial condition, and I need to put that in order to actually define a recursion. So watch out, this definition is not complete. We're going to complete it. We're going to assume that A0 is equal to 1. Once I have that, I can build my sequence using the recursive definition. So what's going to happen for this sequence here? Let me do it in a different color. So for this sequence here, A0 is given to me as 1. Excellent. Then AI is the previous value plus 3. So that means that A1 will be the previous value plus 3. 1 plus 3 is 4. A2 will be the previous value plus 3. 4 plus 3 is 7. Previous value plus 3, and so on. So it looks like the sequences are actually the same. Now, what I have here, of course, is not proof of that because I have no idea what's going to happen in the ... and whether or not this pattern will continue for both of these sequences. So I have to find a more rigorous way to prove that these actually define the exact same thing. But at least it's not obviously untrue. So what we're going to do is we're actually going to use this formula to plug into the recursive definition and check whether or not the equality holds. Okay, let me say this again. We're going to take a recursive definition of the sequence. we're going to plug those values into the recursive formula, and we're going to figure out whether there is an equality there. If after we plug it in, the equality does not turn out to be true, then they don't define the same sequence. So the reason we're going to do that is because the explicit formula allows us to compute any given term. In particular, it allows us to compute term ai minus 1, and it will allow us to compute the term ai. Now, because this is going to be quite a bit of actual calculations, let me actually first write those out. So ai and ai minus 1. So what are these terms according to my explicit formula? So notice that I just have to match up the subscripts, right? So ai means that I'm replacing n with I. So ai is going to be 3i plus 1. ai minus 1 means I'm replacing n with I minus 1. So ai minus 1 will be 3 times I minus 1 plus 1. This is key, okay? This is not 3i minus 1 plus 1. This is going to be wrong. You have to make sure that you're replacing the entirety of n with I minus 1, which means that I'm going to have these brackets, and that is going to make a big difference, okay? Now, I'm going to take both of these terms, and I'm going to plug them in to my recursive formula, and I'm going to check, as I already said, whether or not this equality is actually true. So my left-hand side here is ai, which is this. So my left-hand side is going to be 3i plus 1. Okay, so this is actually ai. Okay, and what about my right-hand side? So my right-hand side is ai minus 1, which is this expression right here. So let's write that out. 3 times I minus 1 plus 1. So this is my ai minus 1. This is ai minus 1. This is ai minus 1. I still need a plus 3. So I'm going to add that on, plus 3. Excellent. Now I just need to make sure that this is an actual equality. Okay, so that is what I'm going to be checking. So let's see how we can do that. Well, all I need to do really is actually expand the brackets out here, do the similar terms, and then I'll be able to check by simply looking at it whether or not the right-hand side simplify is actually equal to the left-hand side. So what do I have here? Let me erase this so that it's clear that I actually only have two sides. So this is equivalent to what? Again, I'm not going to bother changing the left-hand side. I'm going to leave it as 3i plus 1. What about the right-hand side? I have 3i, so let's record that, 3i, and then I have minus 3 plus 1 plus 3. I'm actually just going to leave it, plus 1 plus 3. And the reason I'm going to leave it is because I already know that these 3's are going to cancel because I just wrote down minus 3, and then I could see that I'm going to write out plus 3. And then look, what I have left is 3i plus 1 on the left and 3i plus 1 on the right. So this is equivalent to 3i plus 1 equals to 3i plus 1, which is of course true for any value of i in the positive integers. It's actually true for any value of I altogether. The reason it says positive integers here is, of course, because we wanted those to be our subscripts. Okay, so because this equality actually holds, the left-hand side is in fact the same as the right-hand side, that means that altogether these two different ways were in fact describing the same sequence. Now let's try to do the exact same thing, but with a different formula. So I have the formula for the explicit definition of the sequence, meaning I can just choose a number and calculate that term directly. And I have a recursive definition of the exact same sequence. If you would like to pause for a second here, this is a good chance to practice doing all these things with recursions. First, you can plug in the first few numbers into both sequences and then see if it's even possible that they're the same. And after you've done that, try to follow the same method as we did an example before. So pause, try this for yourself, and I'll be back. Okay, so the thing that we did in the previous example is we have taken the explicit definition of the sequence and we've plugged it into our recursive one, checking whether or not this equality actually holds. Before we did that, because there's a lot of information going on, we wrote out the terms AI and AI minus 1. In this case, it would be CI and CI minus 1, explicitly using the definition of the explicit definition of the sequence. So CI is 2 to the power I minus 1, and Ci minus 1 is 2 to the power I minus 1 minus 1. Okay? Now, these are going to go into here. So the left-hand side is Ci, which is 2I minus 1. So let me highlight the fact that this is just my Ci. And we are trying to check whether or not it's equal to 2 times Ci minus 1. So it's 2 times Ci minus 1 is this term right here. So 2I minus 1 minus 1. This is my Ci minus 1 plus 1 that came from right here. Okay? And so again, as before, all I'm trying to do now is simplify this equation and see whether or not the left-hand side is actually equal to the right-hand side. So what can I do? Well, first of all, I can just open up the brackets on the right-hand side. So my left-hand side is not going to change, and I'm wondering whether or not it's equal to, you know what, I'm going to put these up here too, whether or not it's equal to the right-hand side. So let's open up the brackets here. 2 times 2 to the I minus 1 minus 2 times 1 is going to be 2. And then I have minus 1. Oops, sorry. I already accounted for this minus 1. Never mind. All I have is this plus 1 on the outside. Plus 1. Excellent. Okay, I can see that I can simplify this. This is 2 to the power 1. And when we multiply the 2 powers of the same base, so they both have 2 in the base, we're going to add the powers up. So I'm going to have 1 plus I minus 1. So of course, altogether, this power is going to be I. So this altogether is just 2 to the I. Okay. And then what do I have here? Minus 2 plus 1 is going to be minus 1. And that is fantastic news because I can see that the left-hand side is in fact equal to the right-hand side. So this all checks out, which means that using this explicit definition also made the recursion definition satisfied. So these two different ways actually define the same sequence of numbers. This is how we can check the recursion. Now, what we're going to refer to often is a solution to a recurrence relation. So these explicit formulas are going to be called solutions. Okay? Explicit formula for the sequence. An explicit formula that allows you to calculate any term you want directly. So referring, for example, to this exercise right here, I have this as a sequence. So my recursive definition of a sequence was AI is equal to AI minus 1 plus 3. And my initial condition A naught is 1. This is what we called a recursion, or a recursive definition of a sequence. And the explicit formula for it is A sub n equals to 3n plus 1. This is what we're going to now call a explicit formula or a solution. And the reason we can call it a solution, because these two produce the same sequence. Okay? So this and this produce the same sequence. If they didn't produce the same sequence, we would not call it a solution to this recursion. Okay, it would just be some other sequence defined differently. So for every solution, for every recursion, there is a solution, and our goal for the next little while is going to be trying to actually find such solutions. Solutions, as you've already noticed, are quite powerful because I don't need to pre-compute all the previous terms to compute any term I want. So if I do want to find out what the 10th term is, using the solution, I can figure out directly. Using the recursion, I need to figure out what my first, second, third, all the way up to 9th terms are before I can calculate the 10th term. Recursion is usually easier to set up, but a lot more work to calculate any particular term. So before we dive into developing a very algorithmic approach to solving recurrence relations, which we will do in the next class, we're going to practice noticing patterns and then proving that those patterns actually form a solution. So the idea is to compute the first few terms of the sequence, just like what we have done here. We are going to then try to guess a pattern or a formula. So for example, here, it was kind of obvious that the terms were increasing by 3. So we were adding 3 every single time, not very surprising. And then we're going to actually prove this formula by induction. Okay, let's see how we can crack the Towers of Hanoi example. So from last time, this is the recursion that we've set up. We had that mi is equal to 2 times the previous value of m plus 1, where m1 was equal to 1. So, as per the steps, we're going to compute the first few terms, guess an explicit formula, prove it by induction. Okay, let's compute the first few terms of the sequence. So the first term is equal to 1. That's given to us by default. What's going to be in the next term? So I'm going to plug 1 in here. The formula says it's 2 times the previous term, which is 1, plus 1. So 2 times 1 plus 1 is going to be 3. The next term is 3. Then I plug 3 into here to compute the term after that. 2 times 3 plus 1 is 7. Next up, I plug in 7. 2 times 7 plus 1 is 15. Let's do one more. I plug 15 in. I get 2 times 15 plus 1 is 31. The next step is the hardest because it's not very deterministic, because you literally have to stare at this sequence and try to guess what the pattern is and what the general formula for the pattern is. So if you're looking at these numbers, 1, 3, 7, 15, 31, is there anything in particular about those numbers that you notice? This is not a very easy sequence to spot. The only clue I'm going to give you, maybe before I ask you to pause, is these are the types of sequences that are just a little bit off of the types of sequences we often see in computer science that actually involve powers of 2. Now that I've told you the biggest clue, powers of 2, take a second here, pause, and see, can you connect this sequence to powers of 2? Hopefully, you realize that the first term being given to us isn't actually part of our pattern, and the pattern will start from the second term on. And the powers of 2, what are the powers of 2? 1, 4, 8, 16, 32. These numbers, again, except for the first one, are actually just 1 less than that. So my guess at the explicit formula is that the Towers of Hanoi are just 1 less than the corresponding power of 2. Notice that the second term is second power of 2 minus 1. The third term is third power of 2 minus 1. The fourth term is fourth power of 2 minus 1. So my guess at the explicit formula is that the nth term is the nth power of n minus 1, where n is greater or equal than 2, because again, the first term is actually given to us by the recursive definition. Now, so far, this is nothing but a guess. I have no definitive proof that this is in fact true. The way that I'm going to prove that it's true is by applying induction. So my claim is that this is the formula for the exact same sequence. So as per the few exercises on this page at the beginning, what I can do is then take that and plug this into my recursion to see if it works. Okay, so I could check whether or not this is actually a solution, but we're going to proceed by induction. So what is our basis step? Well, I'm starting with n greater or equal than 2, which means that my basis step will be n equals to 2. So what do I have here? If n is equal to 2, then I'm after the term 3, and that's all I have to check. I simply have to check that this term is in fact produced by this sequence, because the way that I got 3 here is actually using the recursion, Now I just have to make sure that this works. So m sub 2, if I plug 2 into this formula, I'm going to get 2 squared minus 1, which is 4 minus 1, which is 3, which of course is exactly this term, because this is one of the beginning few terms and we've already checked it. Inductive hypothesis, as inductive hypothesis always is going to be assuming that this is true for some k that is above the basis case, so greater or equal than 2. We need to prove that this relationship holds for k plus 1. So we need to prove that m sub k plus 1 is equal to 2 to the power k plus 1 minus 1. Okay? And all of the recursive proofs are actually really straightforward because they give us the exact relationship that we need to prove. So this is like the easiest types of inductive proofs that we saw at the very beginning. All I'm going to do is I'm going to start with the left-hand side. I'm going to change something about it. I'm going to create a sequence of equalities, and I hope to arrive at the right-hand side. So I'm going to start at the left-hand side. So I have m sub k plus 1. Well, what do I have that I know about it? I'm trying to prove that this is the formula for it. But what I have for it is the actual recursion. This defines my sequence. So this is given to me. So what I can do is apply the definition of the recursion, which says that the next term is 2 times the previous term plus 1. So if you wish, this is like applying the recursion where I is equal to k plus 1 here, right? So that I minus 1 in this term is going to be equal to just k. And that's how I get my right-hand side here. So as usual, I'm going to annotate where I am getting these equations from. So this is by recursion. Now this is great news because the moment I go from k plus 1 down to k is when the induction kicks in, because I have an inductive hypothesis that tells me something about the kth term of the sequence. And specifically, it tells me that mk is 2 to the k minus 1. So I can replace my mk with the expression that I have for it using the induction hypothesis. Once I have that, I'm simply going to simplify this right-hand side and see whether or not I arrive at the thing that I'm trying to prove. So what do we have? 2 times 2 to the k. 2 times 2 to the k minus 2 times 1, so minus 2. And then don't forget the plus 1, plus 1. And as in the question before, actually, 2 to the power 1 times 2 to the power k, we add the powers. So we're going to altogether get 2 to the power k plus 1. And then what do we have in terms of numbers? We have minus 2 plus 1, so minus 1, which is exactly the same as the expression on the right here, which means that indeed m sub k plus 1 is equal to 2 to the power of k plus 1 minus 1, as we needed to prove. And therefore, we can state that by the principle of mathematical induction, m sub n equals 2 to the n minus 1 is the solution to the recursion that was the solution to the towers of Hanoi problem. So that means that now, if you tell me the number of disks you have to move from one pole to the next, all I have to do is plug that number into this formula, and I will tell you exactly how many moves you're going to need. So if n is equal to 3, like in our small example from the last page, we needed 2 to the power of 3, so 8 minus 1, 7 moves. And that is exactly what the optimal way seemed to be. If we have 4 disks, it's 2 to the 15th. If we have 5 disks, it's 2 to the power of 5 minus 1, so 31, and so on and so forth. This grows very quickly, which is why in the legend that says that if the monks move 1 disk from one pole to the next by the time they're done, or the day that they're done, is going to be the end of the world. We are in good shape because I believe there's something like 100 disks, and 2 to 100 minus 1 is a huge number of days that we are likely not going to reach as humanity for many other reasons other than the Towers of Hanoi themselves. Another method of guessing the actual formula for the recurrence is to do so by iteration. So instead of having the entire sequence and then guessing what each term represents, thinking about how the pattern forms as we go through composing one term at a time. So let's try it with this example. We have a sequence that is defined recursively this way: 3 times the previous term plus 1. So again, we can compute the first few terms directly. Let's do that. So the first one is given to us as actually just 1. The next one is going to be 3 times this one plus 1, so 4. The next one is going to be 3 times 4, so 12 plus 1 is 13. The next one is 3 times 13, so 39 plus 1 is 40, and so on and so forth. So instead of trying to directly spot the pattern, let's try to think of how these numbers are really formed in a sequence. So here I have a 1. Next up I have 4, which actually straight from the formula came from 3 plus 1. Now thinking about how there is a 3 here and 3 appears everywhere, what else can we do in order to see how the pattern forms? Instead of writing this 4 as a 4, we're going to write it as 3 plus 1 when we sub it into the sequence. Okay, so when we first computed the step from 4 to 13, all I did was plug in 4 into here. We had 3 times 4 plus 1, right? But it's hard to see how the number 13 is then formed. So what I'm going to do instead is I'm going to take this 3 plus 1 and plug it into here, unsimplified as is. So what we're going to have is, as I have written, 3 times 3 plus 1 plus 1. If I open up the brackets here, again, trying to preserve as much of the pattern as possible, what am I going to get? I'm going to get 3 squared. So I'm not going to simplify it to 9 because I want to see the different factors of 3 I'm getting. So this is 3 squared plus 3 and then plus 1. Plus 3 plus 1. Okay, what did I have next? Well, next I plugged 13 into my formula and I got 3 times 13 plus 1. But now instead of plugging 13, I'm going to plug this number, which is of course also just 13, but it looks different, into here. So I'm going to get 3 times that plus 1. Okay, so let's record that. 3 times this entire term goes next. So 3 squared plus 3 plus 1. And then I have this plus 1 on the outside that comes from the recursion. So the trick here too is you can actually see where the recursion happens in these terms, right? It's 3 times the previous term plus 1. It's 3 times the previous term plus 1. It's 3 times the previous term plus 1, and so on, right? So the rule of 3 times the previous term times 1 is very clear when you write it out this way. Okay, if I open up the brackets, what do I get here? I'm going to get 3 cubed from the first term. And then I'm going to get 3 squared plus 3 plus 1. 3 squared plus 3 plus 1. And now the pattern emerges. What seems to happen is I keep the previous term and I add the next power of 3 to it. I keep the entire term and I add the next power of 3 to it. So my guess is going to be that that's how the pattern is formed. The highest power of 3 is 1 less than the index. So if my index is n, the highest power of 3 is going to be n minus 1. And then I'm going to count down from that power all the way down to plus 3 plus 1. And the great news about this is we know what this is. This is a geometric series. Normally we write them from this side on. So it's 1 plus 3 squared plus 3 cubed all the way up to 3 minus 1. This is a geometric series, which also means that we actually know the explicit formula for it. Remember the formulas for the geometric series from the sequences in series part of this unit? What we have is, if I am going to add up the terms of geometric sequence from 1 all the way up to 3 to the n minus 1, then the explicit formula is going to be the next power, so 3 to power n minus 1, divided by r, or the factor that we increase everything by, which is 3, and then minus 1, right? Remember that if I had 1 plus r squared all the way up to r to power n, I had r to power n plus 1 minus 1 over r minus 1, right? So in this case, my n is n minus 1, which is why I end up with the power of n here, not n plus 1, and then I have to subtract the corresponding ones. So make sure you understand where this formula actually comes from by going through the steps to derive it. Now, I can simplify this a little bit because my denominator is simply just 2. So I have 3 to power n minus 1 divided by 2. Great. So this is now my actual guess. My guess is that this recurrence is solved by this explicit formula. S sub n is 3 to power n minus 1 over 2. But that's just a guess. I need to prove it, and I'm going to do so previously the same way as now, by induction. So I have this as the thing I want to prove. My basis step starts with I equals 2. So what's going to happen? I'm going to, or let's call it n equals 2. We usually label this variable as n. What's going to happen? I have to calculate s sub 2 using this formula. So let's plug 2 into here. I'm going to get 3 squared minus 1 over 2. So 9 minus 1 over 2, 8 over 2, which is equal to 4, which is, of course, the exact same number as the one produced by the recurrence. So the basis step checks out. The number produced by this formula is the same as the number that was produced by the recurrence to begin with. For our inductive hypothesis, as usual, we assume that whatever we want to prove holds for k. So s sub k is equal to 3 to power k minus 1 over 2 for k above the basis case, so greater or equal than 2. And I would like to prove that the same relationship holds for k plus 1. In the inductive step, in the actual proof, we're going to, as in the previous exercise, take this formula, start from the left-hand side, and via a sequence of equations, hope to arrive to the right-hand side. So I'm going to start with the left-hand side, s sub k plus 1. In the induction, in order for me to use the inductive hypothesis, I have to somehow make the leap from k plus 1 to k. And that is exactly what the recursion allows me to do, which is why induction and recursion are essentially the same thing in different disguises. Okay, so what I can do here is rewrite s sub k plus 1 using the recursion. So using the recursion, if my I here is k plus 1, then I minus 1 here is just k. So what I'm going to get is, this is 3s sub k plus 1. The k plus first term is 3 times the previous term plus 1. So this is true by recursion. Now, next up is where I'm going to be able to actually apply the inductive hypothesis, because now I have my s sub k. So I can replace s sub k by the induction hypothesis formula. So let's not forget that I am just replacing s sub k. So I have to keep this 3, and I have to keep the plus 1. Okay? So now this step is allowed to happen by the induction hypothesis. And once I have that, all I need to do is actually simplify this expression. There's a number of different ways you can do that, but the easiest one is probably to do the common denominators between this one and this entire fraction. So notice that the denominator here is 2, and the denominator here is just 1. So I'm going to multiply the top and bottom by 2 in order to gain the same in order to gain my common denominators. Okay, so what do I have on the left here is I have 3 times 3k minus 1 over 2 plus 2 over 2, right? This is just me. I haven't done anything. The 3 multiplies to the top, so I just brought it up to the top, and I rewrote this one as 2 over 2. But now that I have the same denominators, I can combine the two fractions. So I'm going to save myself a little bit of space here and combine them together right now. So this is actually what I have, right? Now, let's open up the brackets here. So 3 times 3 to the k is 3 to the k plus 1, because again, the powers actually add together. And then I have minus 3, let's write that down, minus 3 plus 2 all over 2. And what can I do now? Well, now I can, of course, do the similar terms here. Minus 3 plus 2 is negative 1, and I have my over 2. Now, happily, this is the exact same as the right-hand side of the expression I was actually trying to prove, which means my left-hand side is proven to equal to my right-hand side via a sequence of equalities that are justified either by recursion or by the inductive hypothesis, which means that by the principle of mathematical induction, I have proven that the explicit formula for the term of the sequence Sn is indeed 3 to the n minus 1 over 2. Okay, and we're done in this case here. So the thing that you might be asking yourself is, what if you made a wrong guess? What if somewhere in the middle of this process, whether iteratively or just guessing in sequence, you've made a mistake in spotting the pattern and you've spotted something wrong, or you just simply derived the wrong formula? So your formula actually works maybe for the first couple of steps, but doesn't work in general. How will you ever know going through induction that it's wrong? How will the induction actually fail to prove it? So let's take a look at what can go wrong within the induction if your guess was wrong in the first place. Detecting a bad guess. So there's actually 2 things that can go wrong. First, you might not be able to even get through the basis step. And that's going to be a pretty obvious and pretty immediate failure, right? So for example, in here, if I plugged in n equals 2 to the formula and instead of 4 got like a 5, then I would notice that this number doesn't match the number I get from my recursion, and I would know right away that my formula must be wrong. The incorrect basis step is the easiest way to check to detect a bad guess, because it's the first thing that you should be doing. So if it fails, you simply just don't even move on. What if it does work? The basis step works out. What if you somehow get stuck in the inductive step? Let's see what that actually means. So in this case, I have, this is the recursion. The next term is equal to the previous term plus the index. So the index that's on this term. And I have that my initial C0 is equal to 1. The claim is that this is the formula for the general term. So 2 to the power n plus n, where n is my index here. Okay, and that's true for any n above 0. So my basis step is equal to is n equal to 0. And what I have here is that I am given that by the recursion, C0 is equal to 1. Now that's by recursion. So what is my formula that I'm trying to prove actually gives me though? So C0 is equal to 2 to the power 0 plus 0. And what do I have? 2 to the power 0 is 1. 1 plus 0 is 1. So I have 1. So the recursion gave me 1, and the formula gave me 1. So far, so good. 1 is equal to 1. We are in business in terms of the basis case. The inductive hypothesis, I'm going to assume that the formula I'm trying to prove actually holds for k that is above a basis case. So C sub k is 2 to the power k plus k for k greater or equal than 0. And I need to prove that this is the same for k plus 1. So I will be replacing all the occurrences of k with k plus 1. Okay? So here's what I have here. This is what I need to prove. And again, because I have a left-hand side and the right-hand side here, I'm simply going to start with the left-hand side and try to follow the exact same pattern as before. So I'm starting with the left-hand side, c sub k plus 1. The first thing I need to do is get from k plus 1 down to k, so I'm able to apply the inductive hypothesis. The only way to do that is to actually apply the recursion. So by recursion, I'm going to get that, and this, like, you just need to actually plug k for k plus 1 here. We're going to get that this is equal to 2c sub k plus, remember, this has to be the same as the index. My index here is k plus 1, so the thing I need to add here is k plus 1. So this is given to me by recursion. Next, the reason I've applied the recursion is so I can get down to c sub k and apply inductive hypothesis. So I can replace c sub k here with whatever the inductive hypothesis assumed I actually have in my formula. So this is by inductive hypothesis. All I did was replaced c sub k here with the expression that I assumed holds by the inductive hypothesis. Great. Next up came the simplifications and the hope that what I get at the end here is the same as what I want to prove. Okay, so let's open up the brackets. So what am I going to have here? I'm going to have 2 times 2 to power k. So I have 2 to power k plus 1 plus 2k plus k plus 1. Okay, so simply opening up the brackets. 2 to power k plus 1 plus 2k plus k plus 1. Okay, seems pretty good so far. Let me move this over a little bit, give it more room. Okay, what do I have next? Well, let's simplify it. So I have 2 to power k plus 1. And then I have myself 2 apples plus an apple. So overall, I have 3 apples, where apple is k, plus 1. And that's about it. I can't really simplify it much further. So this is now the time to compare what I have and what I want to have. And of course, what I notice is these are not the same. And the problem is they can never be the same. It's not that they're somehow unreasonably hidden, not obviously the same. I can see that 2k plus 1 is the same as 2k plus 1. I can see that 1 is the same as 1. But here I have 3k versus just k. So my expressions can never be the same for as long as k is not equal to 0. If k is 0, then we're good to go. But otherwise, that is not going to hold. So in fact, the only time this ever works is the base case, because that's when k or n is equal to 0. And anything above that will not be true. This is not the same as what I need to prove for any k above 0. So inductive step fails, which means that the thing that I was trying to prove is not true in the first place, which means that my claim here is false. Okay, so it's not that it failed and didn't produce a result. It produced a very strong result. Result being that whatever you claimed was not actually true. So in detecting a bad guess, again, you might have a basis step that is not going to work, and that's the easier scenario because then you know right away not to proceed. Or you will proceed all the way through and essentially at the very end find out that what you're able to simplify the expression to and what you want to simplify the expression to are not equal, which means that what you're trying to prove is not actually true. Now, in the next class, we're going to take a more algorithmic approach to solving recursions so that we won't need to be making guesses and spotting patterns. It's going to be a little bit more straightforward in terms of approaching, but a little bit more tedious in terms of actual algebra.